Yes, it's microphone.
Yeah, it is.
It's working.
It is good.
Yeah. Okay. So the first, where I would like to tell about some changes in the schedule today. Yeah. So Raul is speaking in 6001 in this auditorium, and the Mendes in 4001 is in the block there. And me again here, and Trivedi in the block 4. These are the changes which Raimundo announced. Thank you very much. This is my pleasure to announce today's afternoon first talk by Tomasz Ryszard Pełka, who is from Basque Center for Applied Mathematics, Spain, who is he's currently doing a postdoc fellow in Spain, and his area of interest is singularity theory and algebraic geometry. So the title of his talk today is Equimultiplicity of mu constant families. So please.
Okay. So thank you for introduction. I hope this microphone works. So once again, thank you for the introduction, for the invitation. It's my first time here in Brazil, and I like it very much. So today I will talk about my joint work with Javier Fernandez de Bobadilla, and it will be about the solution to the family version of the Zariski multiplicity question, which was already announced in the first talk of today. So I will work with isolated hypersurface singularities. So contrary to the first talk today, I study hypersurfaces. And by this, I mean I take a holomorphic germ from Cn to C, and I assume that 0 is an isolated critical point, which means that the singular fiber has only one singularity at the origin, and the nearby fibers are smooth. The multiplicity here is easy to define. It's just the minimal degree of the degree of the lowest homogeneous part. And there is also a Milnor number, which is by definition the complex dimension of this algebra. And as most of you know very well, this Milnor number is a topological invariant. I will come to that in a moment. So I will study a continuous family of such singularities. This is simply a family of power series such that the coefficients depend continuously of the parameter. I study continuous families, which are one parameter, but you will also see that for my purposes, we can assume that this family is algebraic, say, over the disk. So the theorem that I'm going to present today is a positive answer to the version of a Zariski multiplicity problem, which asserts that whenever in such family the Milnor number is independent of the parameter, then so is the multiplicity. And this is an old problem and has had many contributions by many authors, and I will not speak about the history because it would require another lecture. But I will make some historical remarks at the end of my talk. So the picture that you should have in mind is like this. Here I have a central fiber, and as I move away from this singularity, some geometry pops out. So the mu constant condition ensures that we have no more singularities in a central fiber, but of course the geometry of this and this might be very different. So now I will recall some known facts about Milnor fibrations, mostly to settle notation. So I start with one isolated hypersurface singularity. The Milnor radius is a small positive number such that all spheres are transversal to the 0 fiber. So as I shrink this sphere, I always cut transversely. And the Milnor fiber is just an intersection of the nearby fiber, which is smooth, with this Milnor sphere. And the theorem by Milnor asserts that the Milnor fiber is homotopically equivalent to a bouquet of mu spheres of middle dimension. So mu is the Milnor number, and you see here that this is a topological invariant. And also Milnor proved that the Milnor fibration is all that you need to know about the topology of singularities. More precisely, the singularity is homeomorphic to the cone over a link. So topologically, this picture is just like I take the intersection of the zero fiber with the sphere and take a cone over it. And in this setting, I define the monodromy, topological monodromy, just by turning once around this little circle in the base and lifting it. And this gives me an isotopy class of a homeomorphism from the Milnor fiber to itself. So an example that you need to keep in mind is very simple. It's the simplest possible. I take the ordinary double point. So the complex picture looks like this. I have hyperbolas degenerating to the union of two lines. But this is a complex picture, and the real picture of the zero fiber is two disks intersecting in a point. The nearby fibers are cylinders. And what does the monodromy do? Well, it turns once around the one axis, once around the other axis, but you see that the product must be constant, so I have to turn in the other direction. So what I get in between is a den twist, which you've seen in the previous lecture. And the point is that when I degenerate, the area when the den twist happens degenerates to the singular point. Okay, so that's the local picture. And now I'm going to study it symplectically. So I take, again, isolated hypersurface singularity. I take the standard Liouville form in Cn, which in polar coordinates has this form. And the differential of this lambda is the standard area form in Cn. This is the Kähler form. And because I started with a holomorphic function, it restricts to a symplectic form on each smooth fiber. And whenever I have such fiber-wise symplectic form, I have a symplectic connection, which means that I can lift any vector field from the base to a vector field here in the source. And I define the monodromy vector field as the symplectic lift of the unit vector field in the base. So this way, I get a vector field whose flow is a symplectomorphism. I define the symplectic monodromy, but there is one technical detail that there is no reason why this symplectic monodromy should map the Milnor fiber, this blue intersection, to itself. In particular, it must preserve area, so I cannot guarantee that I will be still in the ball. I might escape a ball for a moment. And to deal with this, I just adjust the domain, the Milnor fiber a little bit in the following way. So this is a technical detail. So you don't need to understand it really well. It's just a way to overcome this. So I trivialize a collar. Of course, I cannot trivialize all the fibration, but I can trivialize it near the boundary because I'm transversal to the boundary. And this way, by slightly modifying the shape of the ball, I define a closed subset of Cn, which intersects the zero fiber exactly in my original zero fiber, and the nearby fibers are at least diffeomorphic to the Milnor fibers. But now the monodromy maps this red fiber to itself. So from now on, I will skip this technical detail in my discussion. The outcome of this slide is that I've defined a monodromy, which is not only a symplectomorphism, but it's also an exact symplectomorphism. So it pulls back the Liouville. So the difference between the pullback of the Liouville form with the Liouville form is exact. This primitive A is called the action. Moreover, because I trivialized the collar, what I get in the collar near the boundary is the identity. And the triple that I get here, the fiber, the Liouville form, and the symplectomorphism, are isotopic so-called abstract contact open books. So now I will define what I mean by abstract contact open book. For this, I need to recall other general notions in symplectic contact geometry. So I start with a smooth compact manifold with boundary, so like our red Milnor fiber. I say that the form is Liouville if its derivative is symplectic, so like the lambda standard that we've seen in the previous slide. And the Liouville vector field is given by this formula. So it's a unique vector field which solves this equation. Because the lambda is symplectic, this x lambda exists and is unique. And I say that the pair M lambda is a Liouville domain if lambda is a Liouville form, and this vector field that I defined points outwards the boundary. So I need some triviality conditions near the boundary. And now I say that the triple M lambda phi is an abstract contact open book if M lambda is a Liouville domain, and the symplectomorphism phi is exact in this sense, and is the identity near the boundary. So this definition, which is due to MacLean, abstracts precisely the properties of the monodromy that we want, but has the advantage that I can define what is an isotopy of abstract contact open books, that it's simply a smooth family. Well, it's simply a smooth family. And this is the right equivalence relation that I will use. And let me recall that in the previous slide, for isolated hypersurface singularity and a number epsilon such that the central fiber is transverse to the epsilon sphere, I have defined an abstract contact open book. The fiber consisting of the fiber, the standard Liouville form, and the symplectic monodromy. Okay. So now the main point of the whole construction, which will eventually lead to the proof of the conjecture, is to find a good representative of this monodromy. And I have already told you what I mean by representative. I mean representative up to an isotopy of abstract contact open books. And yeah, so let's check it out. I start again with isolated hypersurface singularity. I take its log resolution. So I blow up over the origin in such a way that the preimage is a simple normal crossing divisor. And note that I'm not dealing with a Milnor fiber here. I took what you see for T non-zero in the first picture, in the family picture. And indeed, what I will tell you later that this construction works for arbitrary complex manifold and principal simple normal crossing divisor. Okay, but sorry. So what you usually do, at least topologically, to find a good monodromy, you split the Milnor fiber in this way. So you draw some small boxes at the intersections, and away from the boxes, what you see is an M-fold cover of the corresponding exceptional divisor, or corresponding component of the simple normal crossing divisor. So why it's possible? Well, at least topologically, if I define this di by a local equation z to mi, where mi is a multiplicity, well, the nearby fiber is given by z to mi equals some small delta. So you see that this is an mi-fold cover. For technical reasons, I assume that I've blown up sufficiently many times so that whenever two divisors meet, the sum of multiplicities is bigger than my favorite number m. This can always be achieved by further blowing up. And the main theorem is that there is an isotopy of abstract contact open books from the natural one defined on the previous slide to a nice one, whereby nice, I mean that the fixed points of the mth iterates are precisely the bi pieces, the coverings, for mi which divide m. So you see, I get like an m-fold covering transformations. So whenever mi divides m, I come back to the same point. I get a fixed point. And there are no fixed points in the boxes. And moreover, near these families of fixed points, my symplectomorphism is Hamiltonian. And I will define precisely what I mean by Hamiltonian in the next slide. What you should think of is like a usual rotation. And I can either rotate right or left, and this naturally splits the boundary of the family into pieces, boundary plus and boundary minus, depending on whether I rotate right or left. So this is the main. And note that topologically, it's quite easy to construct such a model, and this was done by Acampo in the 70s. Our input is that you can define this, you can do this picture symplectically. And let's assume that we have this main theorem, and with this main theorem at hand, I will now use Flair homology to prove Zariski multiplicity conjecture. But rather than just throw the definitions at you without any motivation, I will speak more about what is Flair homology. And for this, I will explain you its original source, which is Arnold conjecture. So right now we change the decorations at all. Let's come into the realm of symplectic geometry of compact manifolds. At last, you will see that it's deeply related to Zariski conjecture. So now I will survey the work of Flair in the 70s, which led to the proof of Arnold conjecture. I start with compact symplectic manifold. I promised to define what is Hamiltonian vector, a Hamiltonian symplectomorphism, so here it is. I take type-dependent Hamiltonian, which is just a smooth function from m times the real numbers to the real numbers. And I assume that it's periodic in the sense that when I move by time 1, I get the same thing. And for such a function, I can define a Hamiltonian vector field by this formula. Again, because omega is non-degenerate, there is precisely one vector field which solves this equation. And the Hamiltonian flow is the solution of this system of this differential equation with the boundary condition that at time 0, I don't do anything. And the nice thing about Hamiltonian flows is that by Cartan formula, they are always symplectomorphisms. So I have some periodic orbits here, and the Arnold conjecture. Okay, before Arnold conjecture, I must say what does it mean for a fixed point to be non-degenerate. So here, fixed point of a time 1 flow is what you see here, the starting point of a one periodic orbit, and it's non-degenerate if the Poincare return map has no eigenvalues 1. For a generic Hamiltonian, all fixed points of the time 1 flow are non-degenerate. Now, assuming that all fixed points are non-degenerate, the Arnold conjecture asks whether the number of fixed points is bigger or equal to the sum of Betti numbers. And this was proved by Flair and others, and now this statement as it is a theorem. And the way to prove it was to introduce Flair homology. So let's consider a toy case when the Hamiltonian is time independent. So it just goes from M to R. And I apologize to all of you singularity theorists that now I'm lecturing in symplectic geometry, but I really would like to motivate the tool that we are using to study the Zariski conjecture. So now I will tell you something that you probably already know. Well, for sure you already know, but let me say it nonetheless. In this case, when Hamiltonian is small and time independent, one can show that the fixed points are precisely the critical points of the Hamiltonian. In any case, it's easy to see that each critical point gives a fixed point of time one map because you simply don't move there. And the toy case of Arnold conjecture says that the number of critical points of H is at least the sum of Betti numbers. How to solve it? Well, you use Morse homology. So I should say that this non-degenerate means that the critical points are Morse. So you define a complex generated by the Morse points. So in this example, you have 1, 2, 3, 4 generators. And it's graded by the dimension of unstable manifold, the Morse index, and the Morse differential counts gradient trajectories. So in this example, you have even a number of gradient trajectories joining each 2 points with index difference 1. So in here, you will get trivial differential because the count is mod 2. I should have mentioned this. Yeah, I've mentioned this. The complex is generated over Z2, and the count is mod 2 count. So this is the formal way to state it. The moduli space of the Morse trajectories, well, consists of maps satisfying the Morse equation with boundary conditions that it converges to one point and the other at plus and minus infinity. Yeah, so this is what I've told you. The differential is the count mod 2 of the Morse trajectories. And the theorem, basic theorem in Morse theory, asserts that the homology of the complex that I've just defined is the usual singular homology of the manifold. So now I can prove the toy version of Arnold conjecture. Well, the number of critical points is the number of generators of the complex. So it's for sure bigger or equal to the number of generators of the homology. And by the theorem, this rank is sum of the Betti numbers. Okay, so this is something that you know, but the idea is to generalize it to the case where H is time dependent. So let me generalize it in 2 cases. First case is for the Arnold conjecture, where I work with compact symplectic manifold. And the second case will prepare me to prove the Zariski conjecture. And I start with the abstract contact open book. So the Liouville domain with an exact symplectomorphism. And the discussion will be parallel. Now, the left column is basically work of Flair, and the right column is the work of Seidel in the beginning of this century. And all the details were rigorously stated and proved in the recent work of Uljarevich. Okay. And in this case, I assume, for the sake of simplicity of presentation, that the manifold is aspherical, which was the original Flair setting. So in each case, I start with time-dependent Hamiltonian, and I assume some non-degeneracy conditions. So I told you what the non-degeneracy means. Here, well, here it means the same. The Poincare return map has no eigenvalues 1. And here I assume periodicity. Here I assume twisted periodicity. So when I move time by 1, I get what I would get by my chosen symplectomorphism. And because the symplectomorphism is trivial near the boundary by the definition of abstract contact open books, I also assume that this Hamiltonian has small negative slope near the boundary, which basically means that I just rotate slightly. Near the boundary, I have trivialization by the Liouville vector field, so it makes sense to say about rotation, and I assume that I only slightly rotate counterclockwise, I guess, or clockwise. There are different conventions in literature. Anyway, so before we did Morse homology on the manifold, now we do Morse homology on a certain loop space with respect to some action which will play the role of the Morse function. The loop, what is the loop space? Here I just take the contractible loops. Here I take twisted loops. So the paths that start with at the point and end in the image of this point by my symplectomorphism. So for the fixed points, I get loops, but of course, I might get some paths like this. The action functional is given by this horrible integral. Here I must say what is this V, because my manifold is spherical, I can feel the, because I take contractible loops, I can fill the loop by a disk and integrate the symplectic form, and because of this assumption, this number is well defined. And on this side, I just use Stokes' theorem. And so I integrate the primitive along the loop. And what you see here is a Hamiltonian, and what you see here is this action function. So we had this exactness condition that phi upper star of lambda minus lambda is minus dA. So this is dA. This is this function. I define a complex, as in the previous slide, generated by the critical points. And it turns out that the critical points of the action functional are precisely the Hamiltonian loops. So the paths, the integral curves of the Hamiltonian vector field. And the moduli space of trajectories that I'm counting is exactly as in the previous slide. So I count now time-dependent trajectories subject to some two conditions. The first condition is the periodicity. So here I have usual periodicity, so I count maps from a cylinder. And here I have twisted periodicity. So I count maps from a strip, and the strip is glued by my symplectomorphism. And the flare equation, which is an analog of a Morse equation, looks like this. You will see that it specifies to the Morse equation in case of time-independent Hamiltonian. And here, this JT is an almost complex structure compatible with omega, satisfying again usual periodicity in the compact case and twisted periodicity in this twisted case. So this is, these are the definitions, and how do I use these definitions to prove the conjectures? Of course, here there is a theorem that d square, that the differential is 0, so it gives a well-defined complex. These are some deep theorems. And also, I totally skipped the part about grading. Grading is some Conley-Zender index, which I don't have time or will to define today. How to prove Arnold conjecture? Well, I start with compact symplectic manifold. I take time-dependent Hamiltonian. I have flare homology from the previous slide. The theorem. Flare homology does not depend on the choice of Hamiltonian. Once I have this theorem, I can choose Hamiltonian to be time-independent and small. So then the trajectories that I count are time-independent. So this picture, counting the maps from the J-holomorphic maps from the cylinder, becomes this picture, counting the Morse trajectories. That's because when this guy vanishes, I just have minus Jx, which is gradient for the metric associated to the symplectic form. So the flare equation becomes a Morse equation. Now, so the flare complex for this particular choice of Hamiltonian becomes the Morse complex. So flare homology becomes the usual homology. And now the number of fixed points, which generated the flare complex, is, well, is at most the rank of the flare homology. It's at least the number of the rank of the flare homology. So exactly as for the time-independent case, I proved Arnold conjecture. So now let's go back to singularity theory, and let's see how far we can go by using these ideas towards computing flare homology of the symplectic monodromy. So in general, I start with an abstract contact open book. I defined fixed point flare homology as a homology of this flare complex generated by twisted loops, which generalizes the flare complex for the compact case. Theorem here is that the flare homology does not depend on the isotopy class of an abstract contact open book and the choice of this auxiliary Hamiltonian. But there is an important caveat. We impose this twisted periodicity condition. So unless phi is an identity, we cannot choose H to be time independent. So no royal way, no shortcut like in the previous case. But remember the main theorem. In our case, when we studied this good representative of symplectic monodromy, we had a picture like this. We had a huge families where phi is the identity, huge families of fixed points. So, and moreover, the diffeomorphism was Hamiltonian near these families. So inside the families, I can choose H to be time independent. I cannot guarantee that it's time independent in the white pieces, but in the blue pieces, it's very nice. Of course, I cannot say that the Morse, that the flare complex in the blue pieces is the Morse complex because I don't have a flare complex in the blue pieces. The flare complex count trajectories which might travel from one piece to another. Nonetheless, I can filter the flare complex by an action. The action was, and the action was some integral, but in this near these blue families, this action was, you remember, some integral minus the integral plus the action function. And this action function, so these integrals depended on the Hamiltonian, so I can choose Hamiltonian to be very small, and this action of the loop is close to the action function. So roughly speaking, I can filter my complex so that the graded piece corresponds to the blue piece, or more precisely to the disjoint union of some blue pieces which has the same action function. This leads to a Morse bot type spectral sequence, which was found first by MacLean. So the spectral sequence associated to this filtration converges to the flare homology, and its first page is the relative homology of the blue pieces. Well, basically because here the Hamiltonian is independent of time, so the graded piece is like the piece of the Morse complex. So yeah, it counts the relative homology. Moreover, in our case, which comes from singularity theory, we will see that the boundaries are all of the same type. I have only boundary plus, so I get just BI modulo its whole boundary, or in other words, the Borel-Moore homology of BI. So let me formulate this more precisely. I start once again with isolated hypersurface singularity and fix a number m that I will study. I will study mth iterate of phi. I take an m-separated log resolution. So its m-separated condition means that when two divisors meet, the sum of multiplicities is bigger than m. And again, I split the Milnor fiber into these pieces, which I denote by BI. Now the MacLean spectral sequence, well, the spectral sequence which we call MacLean spectral sequence asserts that there is a spectral sequence converging to the Floer homology, so that in the first page you'd see the Borel-Moore homology of the BI which correspond to the fixed points of the nice representative of the monodromy. So to those i's are that Mi divides M. And this is some strange shift that you don't really need to care about right now. What is important here? If I consider the exceptional divisor, then this BI is an open manifold. And it is a covering of the divisor minus the intersection point with the others. So its Borel-Moore homology is non-zero. If I look at the proper transform of the fiber, of the singular fiber, this corresponding BI is homeomorphic to the singular fiber minus the singularity. And because I take this blue piece and remove what I find here. So by the conical structure theorem, if I start with a Milnor radius, then this B0 is just a cone over the link minus the origin. So its Borel-Moore homology vanishes because it, cone contracts to its base when I remove the vertex. So we have this spectral sequence. And how to conclude from this spectral sequence? Well, I start with the mu constant family like this. I fix a Milnor radius for F0 and define this fiber and note that I intersect with this red ball, which was this modified ball to get symplectic monodromy, but I don't care about it right now. I get, by gray stability, by definition, By definition, I get an isotopy of abstract contact open books from this abstract contact open book to this one. The first one occurs as a Milnor fibration. The second one occurs as something that is not a Milnor fibration because it takes place in a ball which is too big. You see that this guy is not a Milnor ball. But nonetheless, between the Milnor ball and the big ball, what I see is a cobordism, which is homologically trivial. Well, this is a relatively easy fact proved by Lera Manujan in the 70s and follows from exact sequence of pairs and stuff like that. So now this concerns the family. Now I fix a member of the family and take the log resolution of this fixed member. I do not take any common resolution. I have no reason to expect a common resolution. But I fix T and resolve it. And I look at the MacLean spectral sequence. So, I'm sorry, the mask. As in the previous slide, I recall that whenever I take the proper transform of the fiber, the contribution to the spectral sequence is 0. Now, I told you in the previous slide that this is true for the Milnor fibration by the conical structure theorem, but here it's also true, right? Because I have something that contracts something whose Borel-Moore homology vanish, and I glue a homologically trivial cobordism to it. So still, homologically, I get something trivial. And when I look at exceptional divisors, then its multiplicities in the resolution are at least multiplicity of the singularity, and the contribution to the spectral sequence is non-zero. So what is the conclusion from these 2 points. Whenever I'm smaller than multiplicity, then what I see in the spectral sequence is only the contribution from this proper transform, because everything else has too big a multiplicity to fit here, to satisfy this condition. So, and I've told you that the contribution from the proper transform is 0. So the Flair homology that I get is 0. And if I'm exactly at the multiplicity, I can arrange my resolution so that I only see one divisor here. Why? Well, I blow up at the singularity. I get something of multiplicity equal to the multiplicities of singularity, and then I blow up at singular points. So I get bigger multiplicities. So only the first blow up matters. So my spectral sequence has only one column, and as a result, it degenerates to something non-zero. So I arrived to the following beautiful formula that the multiplicity of Ft is the minimal number m such that the Flair homology of the mth iterate of the monodromy is non-zero. Now, because I had, and note that it worked not only for the Milnor fibration, but also for any member of a mu constant family. So, because the Flair homology is an isotope invariant, the right-hand side of the formula is independent of T. So the left-hand side is independent of T. This is then the end of the proof. So some remarks are in order. The spectral sequence like this for the Milnor fibration was constructed 3 years ago by MacLean, who proved this beautiful formula for phi being a symplectic monodromy for the Milnor fibration. Actually, he used Milnor fibration in the sphere, not in the tube that I use all the time. And he achieved this by totally different methods that I will be happy to explain you maybe after the talk. What's important is that his method does not generalize to this case to this member. He basically studies the link, and the link here and here might be symplectically very different. So our contribution is to construct this model, this, we call it radius 0 model, which gives a good representative of the monodromy. And this allows to obtain this formula for any member of a mu constant family. This nice model, I've already told you, was constructed topologically first by Acampo, who used it to compute the Lefschetz number of the monodromy. And when you look at this model, this Milnor fiber splits into pieces, you relatively fast can see that the Lefschetz number is the sum of Euler characteristics of Bi. So this formula is kind of generalization of this formula. This formula proves a weaker version of this. It proves that the multiplicity is at most the minimal number m such that the Lefschetz number of the mth iterate does not vanish. There is a typo here, it should be non-zero. However, this inequality does not prove the Zariski conjecture because the inequality may be strict, and it is strict even in this simple case. You take the ordinary double point in 3 dimensions, and then the Lefschetz number of the second iterate is the Euler characteristic of the Milnor fiber, and it's 0. Well, so the point is that topology does not see the multiplicity in this sense, but the symplectic geometry does. And it's kind of a good advertisement to look at symplectic geometry of the singularity. And last but not least, I would like to say that our construction actually works in much bigger generality and gives this spectral sequence for any holomorphic function from Y to C, where Y is a Stein space with isolated singularities. So I can even allow some singularities of the ambient with the small technical condition that for surfaces, I want only using Q-homology sphere links. This is to achieve the exactness of the symplectomorphism. Well, the Liouville form here is the standard Liouville form that I use in such a setting. And the Milnor ball is a sublevel set of this. So the Liouville form is minus dc of the Purish-Holomorphic function, and the ball is the sublevel set of this function. So this is like a generalization of the usual ball with some modified distance function. Okay, so since do I have some more time or? Okay, so I will not tell you the details about the construction, but let me just state what the construction does. So how do we construct the symplectic monodromy? I start, and in which generality does it work? I start with a complex manifold. I take holomorphic functions such that the singular fiber is simple normal crossings. So this can be a resolution of singularities of an isolated singularity like this. But you see that if I allow several singularities, I also can resolve and get a similar picture. And the construction will work. So take omega x to be a Keller form in X. So if this X, if this picture comes from a resolution of an isolated singularity or of multiple isolated singularities, then I take a form like this. This is just an example. So I pull back the standard from here and I modify it a bit so that I get a non-degenerate form here. But I can start with other Keller forms. And if you are interested, for example, in the generation of compact Calabi-Yau manifold. So again, you take this fiber would be a Calabi-Yau manifold, and this will be its degeneration. You can take omega x coming from the from the Calabi-Yau metric. If you are interested in there are many settings where such omega x can be chosen. Again, I write this singular fiber like this. I assume for technical reasons that this D is M separating in this sense. And our goal, which is achieved in our paper, is to construct a smooth manifold with boundary A. This A stands for the Acampo space, such that away from the boundary is just the smooth part, so the part which is not touched by the resolution. And we construct a fiber-wise symplectic form for any positive delta, such that here, away from the origin, this omega A delta, it should be omega A delta here, is a pullback of omega x from X. But at the origin, I glue a small circle here. So I take the real blow up, and over this small circle, the symplectic monodromy of phi, defined as a time one flow of the symplectic lift, is precisely as you would expect. So inside Bi is a rotation. So I get a fixed point whenever Mi divides M, and in between, I get a then twist. So the fixed point locus is the disjoint union of Bi. And this is the picture of our construction. So I have one minute to show you what happens in this picture for the simple example of this form. So this is the singular fiber, 2 disks meeting at the point, and the limiting monodromy is the identity in one axis and flips the other axis to the other side. So these blue lines are what happens with the front ruling. Step one of our construction, we take a real blow up. And you see that the monodromy, which, well, is quite nice in these pieces, does not glue continuously. So here we introduce some tropical coordinates to parameterize the dual complex and insert the piece of dual complex in between, and then take a fiber product of these two pictures, and we get a beautiful interpolating dent twist. So once again, this picture was achieved by Acampo topologically, and what we do is to introduce very specific coordinates, tropical coordinates, on the dual complex to be able to introduce an explicit symplectic form here, which does the job. And with this, I would like to conclude.
Hi. This radius zero model of the monodromy seems to be a very powerful tool. So my question is, what about other invariants of the singularity? For example, Hodge numbers. Do you expect to have some relation, some way to compute the Hodge numbers from these techniques? Or?
What do you mean by compute? So
yes, to relate, for example, when you have the mixed Hodge structure and the monodromy, then you have the eigenvalues, the generalized eigenvalues space, and then you have this model of the monodromy, and then if you can translate this in the Floer homology in some way in pieces.
Yes, not necessarily using Floer homology. The whole idea is that this radius zero model allows for simple explicit computations. So you can compute the properties of symplectic monodromy at radius zero and then use symplectic connection to move these properties to the positive radius. So let's look at this picture. Here, over the red circle, you have a beautiful dynamics, you have the formula, you can compute, and whatever you can compute, you can then take the radial vector field and lift it symplectically and move to the area where the monodromy is the natural one. So certainly, yes, you can. We didn't try, but you can perform some computations and see what it gives.
Okay, thank you.
So mine is a simple question. So to my understanding, non-trivial symplectic structures can only be defined in even dimensions, since in odd dimensions they collapse by their own hypothesis. So then, how do you construct a Floer homology on odd dimension?
We don't. Oh. This form is fiber-wise symplectic. It's symplectic on each fiber. Oh. Fiber is an even dimensional manifold. Of course, we don't have a symplectic structure in the whole boundary of the Acampo space because it wouldn't make sense.
Thank you very much.
You mentioned in your preprint that you have perhaps other applications in mind for monodromy at radius zero. Do you want to say anything about those?
So what are the? So what is your question precisely? What are the applications of the monodromy at radius zero?
Right. Other applications of monodromy at radius zero.
So let me think. There are, for example, this is something that we are currently exploring, so I cannot promise you that everything will work. But you can, for example, try to modify this construction to define a link at radius zero. So instead of studying Milnor fibration, you don't have a function. You have an isolated singularity, and you take the strictly pure subharmonic function, and well, you decrease it. You decrease like a ball around the singularity, and you perform this construction replacing the this f by this strictly pure subharmonic function. And if you can perform all this construction, you get something that models a link at radius 0. And this should, again, you can study the dynamics. Now you don't have the monodromy, but you have the Reb vector field. And you study the dynamics of the Reb vector field. And it should, for example, well, you can try to compute the contact homology of this. So this should give a tool to compute contact homology of the link. And you have different flavors of contact homology. You have embedded contact homology in dimension for surface singularities. You have cylindrical contact homology. You have usual contact homology of symplectic field theory. And we do expect that this kind of construction will allow to compute, or at least to formulate MacLean-style spectral sequences converging to these homologies. This is now work in progress, and probably it collapses, but we don't know. In any case, as I've explained in my previous answer, the point is that at radius 0, you can compute things. Things become canonical. Yeah, so that's all I can say now. In a short answer.
Okay, thank you. So what's the main difficulty if you want to prove the topological invariance of the multiplicity, not for families, but just for two functions you have?
That's a good question.
So, because you have a isotopy, no, of the abstract
well,
open book.
We don't.
No?
That's
Yeah.
the point. So let me remark that I should have said it, that there do exist examples of singularities with the same topological type, but which are not connected in a mu constant family. And for such two examples, the Zariski conjecture states that they have the same multiplicity, but we don't have a way to compare. We don't have a way to compare flare homology. So of course, flare homology will compute the multiplicity of one and another, but in principle, there is no way to relate one. And it's a very it's a very good question, right? Just to try to apply these methods, we don't have any idea how it should work.
No more questions, so let's thank speaker again.
Ah, eu preciso de... Sim. Já vou colocar.
Já ia apresentando.
Só um momentinho. Ah, tenho que gravar você mesmo falando. Mesmo hablando fuera. Perfeito. Deixa se está aceso, tá.
Raul?
Espera, Paulinho. Ele vai subir a tela, né?
Paulinho?
Vai subir a tela, né? Sim. Quando você quiser.
Good afternoon. It's my pleasure to introduce Professor Raul Setsinha from Universidade de Valencia, Spain. Raul's areas of interest are singularity theory and differential geometry, with emphasis on the study of germs and multi-germ classification problems, topological invariants of stable maps, and geometry of singular surfaces, among others. The title of his talk is The Axial Curvatures for Coronculae singular n manifolds in Rn plus k.
Thank you very much, Bruna, for your generous presentation. It's a pleasure to be here in Sao Carlos again, finally, after this pandemic. And it's a pleasure to be able to give a live talk, I think. It might be my first live talk after the pandemic. So thank you for that. I know I only have half an hour, so I had to write down some definitions before. So as Bruna said, the title is of axial curvatures for singular and manifolds in Rn plus k. Our goal is to define second-order curvatures, kind of principal curvatures for singular manifolds. Some have been defined, or many have been defined for surfaces, but the way in which they were defined for surfaces depended on certain things that are particular to surfaces. So how to generalize that to other dimensions was not clear at all, and that's what we've managed to do here. This is a joint work with Pedro Benedini Riul and with Jorge de Olindo Silva. So the setting is the following. What do I understand by a Coranguan singular n manifold? Well, it's basically, we have here Rn, a point in an open neighborhood, and F, a parametrization, which has a singularity of Coranguan at Q. The image of Q is P, and this is the notation I use for this singular manifold. But all our curvatures are local, okay, at a point. So how do you define a first fundamental form at a singular point? What you do is you consider not the tangent space in Rn plus k, but you consider the tangent space of Rn, okay? And you define the first fundamental form of two vectors in the tangent space of Rn, not of the singular manifold, as the differential of f acting on u and the differential of f acting on v, the scalar product. So obviously, since f has corank 1, this does not give a metric, it gives you a pseudometric, okay? Because there can be non-zero vectors such that the first fundamental form of u is equal to 0. So this is a pseudometric. And we can also define the second fundamental form, and it's just defined the image of two vectors u and v is basically taking the second order partial derivatives and projecting to the normal space. What you do basically is you define it on the base of the tangent space as the if you have the image of the partial with respect to xi and the partial with respect to xj will be the partial derivative with respect to xi, xj, and take the normal component. Okay, this is defined on the base, and then you extend it in a unique way as a bilinear symmetric form. Okay, so the unitary tangent vectors, since we don't have a pseudometric, this is not a sphere. Okay, this has a different shape because we have a pseudometric. I will show you what shape it can take. And we define by delta p the image of the unitary tangent vectors by the second fundamental form. Okay, so this lives in the normal space of the singular manifold. This is what is called the curvature locus, and classically it's been defined for surfaces in R4, regular surfaces in R4, where it's called the curvature ellipse. And this curvature locus, it codifies all the second-order geometry of the manifold. Okay, and we define the affine space as the affine space of minimal dimension, which contains the curvature locus. Okay. Okay, so for example, if we have a Monge form, and by Monge form, I mean that the parametrization is of the form of this form, where obviously if it's corank 1, we can always take it to something like this, where the fi don't have linear part. Okay, this is what we understand by a Monge form here. And if f is given in a Monge form, then you can see that the unitary tangent vectors satisfy this equation over here, which means that the unitary tangent vectors are a sphere. Okay, sorry, not a sphere, a cylinder. Okay, I'm missing xn here. This is a cylinder. What's happening, the difference between the regular case and the singular case is that, well, I don't want to get too much into this, but in the singular case, every singular manifold can be seen as a projection of a regular manifold in a tangent direction, an orthogonal projection in a tangent direction. When you project in that tangent direction goes to infinity in the singular manifold. So if you have the sphere of unitary tangent vectors, this is a kind of blow up. That direction has gone to infinity, and you obtain a cylinder instead of a sphere. Okay, and in this case, the curvature locus is very easy because it's just taking the 2jet such that this is satisfied. Okay, this is the parametrization of the curvature locus. Okay, because the coefficients of the second fundamental form just depend on the 2jet of this part over here. Good. So let me give some, I'm going to say historical background, but it's not very historical because all this is very recent. I mean, not only my talk, but the historical background is very recent also. So what happens for singular surfaces in R3? Well, here the curvature locus can be a parabola, a half line, a line, or a point. Okay? So myself with Kentaro Saji, we define the following curvature. If you have in the normal space you have your curvature parabola, you define the axial vector as the vector perpendicular to the directrix of the parabola. Okay, and what you do is that you project on that direction, and the value of this projection is what we call the axial curvature. This axial curvature is given by the minimum of the scalar product of the second fundamental form with the axial vector, which I call VA, okay? Where U is a unitary tangent vector, okay? So this is just the projection on the axial vector, okay? This is how we define this curvature. This, by the way, is the, okay? And I will say something about this curvature, but let me first introduce another curvature, which was given by Nuño Ballesteros and Martins. Sorry, Martins and Nuño Ballesteros, which is, for example, when the curvature locus is a half line, something like that, you can define the projection over here, and they called it the umbilic curvature, which was given by the scalar product V2, where this V2, absolute value they gave, where this V2 is just, here we have the axial vector, and here we have an orthonormal frame, okay? V2 is an orthonormal frame for the normal space, okay? So they defined this curvature over here. They called it the umbilic curvature. And again, it can be seen as a projection, okay? This idea of projecting the curvature locus is in fact not new, because in the regular case, when people have studied the curvature ellipse, if you choose in the normal plane a certain normal direction and project in that normal direction, you get a segment, and the two extremal points of the segment are the principal curvatures in that direction, okay? So in a way, these are a kind of principal curvatures. And in fact, these are interesting because this axial curvature, it captures flat geometry, that is contact with flat objects, and this one captures round geometry. And for the case of frontal type singularities, which is a generalization of wavefronts, for frontal type singularities, we proved that the axial vector or axial curvature is the singular curvature defined by the Japanese, which is a generalization of the geodesic curvature, but for singular surfaces. So, for example, many people have worked with this singular curvature, and they've proved Gauss-Bonnet theorems for singular wavefronts and things like this. And this is a generalization for any corank 1 singularity, not only wavefronts or frontal type singularities. And the umbilic curvature is a generalization of the limiting normal curvature, also defined by the Japanese for singular frontals. Okay, so you have interesting theorems like this: this squared plus this squared equals the curvature squared of a certain curve, things like that. Okay, so this was what has been done quite recently, but as you see, it all depends, in order to define these curvatures, it all depends on how we define this orthonormal frame. Okay, we have to choose the axial vector and complete it to make an orthonormal frame. Okay, and how did I choose the axial vector? Using the properties of the parabola. What happens when I go to higher dimensions? The curvature locus is not a parabola anymore. It can be, for example, a surface with singularities. So how do you define the axial vector? Or how do you define a proper, interesting orthonormal frame in which to project to obtain meaningful curvatures? So that's what we have done. So in the general case, I need some definitions. First of all, I call L the minimum of n and k plus 1. What is n? N is the dimension of the tangent space of Rn, obviously, and k plus 1 is the dimension of the normal space of the singular manifold. And I define the axial space at P, which is a subspace of the normal space, as the affine space if the dimension of the affine space is equal to L, and it is any L vector space containing the affine space. Otherwise. Okay? So basically, I want to define, sometimes the curvature locus is degenerate, and even if the normal space is very big, the curvature locus can be a line. Okay? So in spite of that, I want to be able to define several curvatures. Okay? So this is why I define this axial space, which has this dimension, which is the amount of axial curvatures I'm be able to define, more or less. And here comes the key point. I want to define the axial vector. How am I going to define the axial vector? The important thing was to realize that this axial vector, in the case of surfaces, is the image by the second fundamental form of a null tangent direction. That is, the tangent direction such that the first fundamental form acting on it is 0, the image by the second fundamental form of it is the axial vector. And this I can define in other dimensions. So I have a vector, we call it a null tangent vector if that is 0. And now suppose that the image by the second fundamental form of this null tangent vector is different to 0. Then we can define the primary axial vector as VA1, this image, okay? This is how I can define it. I'm using this hypothesis. Obviously, this could also be 0. In that case, there are also ways of defining it, but I'm giving 0 details in this talk because I only have half an hour and I've spent already, what, 20 minutes? 10 days? Ooh, I've got to run a little bit, okay. So once I have this first axial vector, I have to complete the basis to obtain an adapted frame. How do I complete it? Well, that is not easy, and you have to specify in each case how you do it. For each nk, you have to specify how to complete the basis. But once you have it, you obtain an orthonormal basis for the axial space. So now I can define the RE axial curvature as kappa A sub I P, the critical values of where is a unitary tangent vector. Before I define the axial, for surfaces, I define the axial curvature as the minimum of the projection. But when you have more dimensions, you can have more than one critical value, and all of them are important. So this is how we define our axial curvatures, but there are many. How many? L times n minus 1. Where L is what I defined before, and n minus 1 is n minus 1. So there are those many curvatures, and the notation I use is this one over here. I stands for the vector I'm using, and J stands for something between 1 and n minus 1. Good. So some results. For singular surfaces in R2 plus K. Here, the situation is similar to surfaces in R3. And for K equals 1, I have the axial curvature, and for and the umbilic curvature, obviously. And we have formulas. Well, I'm not even going to write that. We have different formulas to calculate these curvatures in terms of the coefficients. And in the case K equals 2, for example, that is singular surfaces in R4, we have, if K is the curvature of gamma of t equal to f of t 0, for certain, when you have a Monge form, okay, suppose it's a surface, so you have x, y, f1, f2, okay, I consider f of t 0 for certain, no details, but the thing is, we have k squared okay, and we also have that, to make it short, the sign of the primary axial curvature determines the type of singularity of the height function in the direction of the primary axial vector. I would write that in more detail, but I have no time. I want to go to the interesting cases. But it captures flat geometry. Okay, so when it's positive, you have an A1 singularity, an A1 plus, or an A1 minus. When it's negative, all that. Okay, let's go to the interesting cases, which are higher dimensions. So for three manifolds, for example, when three manifolds in R4, for example, singular three manifolds in R4, the curvature locus is a planar region, which can be something like that, which goes to infinity, and it's basically an ellipse, which is repeated many times. And we have classified all the types of curvature locus that you can have. And for three manifolds in R5, we have also partially classified them. And we have formulas also to compute them. But the most interesting thing is that if we consider a regular submanifold so this is a three manifold. So you have three variables, x, y, z, and it's singular. But if you consider f of x, y, 0, you have a regular submanifold inside the three manifold. A regular two manifold inside the singular three manifold. And it turns out that our axial curvatures coincide with the BAI principal curvatures of the regular manifold. In most cases, sometimes you can have more axial curvatures than principal curvatures of the regular manifold, but when it's possible, without details, they coincide. So in that sense, these curvatures are a type of principal curvatures for singular manifolds. And this gives many interesting corollaries. Well, the idea of this is you have your unitary tangent vectors, second fundamental form. You have here your axial, your curvature locus, and it turns out the critical values are somewhere over here. Okay, so what happens is that if you consider the restriction of the second fundamental form to this S1, this restriction gives you this ellipse over here. It's a regular manifold, and it has a curvature ellipse. And it turns out that these critical values of this one coincide with the critical values of the restriction, which are the principal curvatures of the regular manifold, more or less. So, interesting corollaries. If you have a 3-manifold in R4 for certain orbits, the Gaussian curvature of the regular manifold is equal to this formula of our axial curvatures. Okay. This includes, for example, frontals in higher dimension, frontals from 3 manifolds to R4. And in certain cases, for example, if you have a cross-cap curve in R4 or a swallowtail curve, that is a curve of swallowtail points or a curve of cross-caps, which are singularities from C3 to T4 or R3 to R4. You have, in this case, the curvature of that curve is one of our axial curvatures. The curvature of this curve is also one of our axial curvatures. Okay, so basically, it turns out that all the second-order curvatures, which have been defined for surfaces, are one of our axial curvatures, and basically all the second-order geometry can be recovered from our axial curvatures. That is more or less the idea. There are many more results. I'm stating just a couple, but the paper is quite long. And just to finish, in the last minute I have, there is also a curvature called the umbilical curvature, which has been defined for regular surfaces and for singular surfaces, which is defined as the distance of P to the affine space. And basically, this tells you the focal set, gives you the focal set, the distance to centers of spheres with the generate contact with the manifold. It turns out that if the codimension of the affine space is equal to R, then the umbilic curvature is precisely the absolute value of this curvature over here. So basically, all the curvatures, second-order curvatures that have been defined and are known are included in these axial curvatures, and they basically give all the second-order geometry. And I think one can go much further, but I don't have any more time. So thank you very much for your attention.
Thank you, Raul, for the talk. Are there any questions or comments for Raul? Cidinha?
Just a question. Just a question concerning notation of your regular surface.
Yeah.
You assume that you have a normal form for
Molds.
the current one surface, singular surface, in such a way that Z
Exactly.
is the kernel, and
Yes.
then you take Z equals 0.
Exactly.
That's
Yeah,
okay.
that's it.
Just
So
to
it's
make
the
sure.
Monge form. This would give x1, xn minus 1, and then f1 of x1, xn minus 1, 0, and the same with fk plus 1.
Okay, thank you.
More questions?
By the way, Sidinia, this, for example, from 3 minus 4 to R4, you can have a surface of cusp points, a cuspidal surface. This regular submanifold is the surface of cusp points.
Matthias?
At some point, you mentioned that you need frontal singularities, right? Do you need it for all these results? No.
No. What I'm saying is that I'm generalizing what is done for frontals.
Okay.
But for some examples in particular, for example, when you have here, if you have something in this orbit, okay, which is the 2-jet is equivalent, A2 equivalent to this over here, then what you have is a cuspidal surface maybe, or well, not only a cuspidal surface, but it can be in most cases a frontal. So in particular, this can be used for frontals. But this is in general for any core rank 1 singularity.
Okay. Yes, and then there's again the question: Did you look into how this might be related to other curvature theories?
Yes, exactly. You asked me this in my last talk. In the last Sao Carlos workshop online, I talked about the surface case, the axial curvature.
Right.
And you asked me if it was related to Lipschitz-Killing curvatures. At that moment, I had never heard about Lipschitz-Killing curvatures. So I started reading a little bit, not much yet. But maybe in surface case, it wasn't easy to see. But in the general case, now, my first answer will be yes, it is related some way. But I still don't know. I mean, in the regular case, the Lipschitz-Killing curvatures are given by products of principal curvatures. So I can maybe define some Lipschitz-Killing curvatures giving products of axial curvatures. I don't know, and maybe Nicolas can help us with this, if Lipschitz-Killing curvatures have been defined for singular manifolds. If not, this would be a way.
Okay, thank you.
Okay, let's thank Raul again. Good afternoon. It's my pleasure to announce the second lecturer of this season, this time. He's Professor Ionesco from the Institute of Mathematics, Polish Academy of Science. He's the director of the Stefan Banach International Mathematical Center and the director of the Center for Advanced Studies, Warsaw University of Technology. The title of his talk is Symmetrizations, Transforms for Curves of Curves and Surfaces.
Thank you. Thank you very much. So first I would like to thank organizers, Sidinia, Regilene, Raimundo, Anna Claudia for so much work and help to come here and again to be here and meet these our friends. Thank you very much. My talk is devoted to Osamu. It will be a relatively easy talk, I hope. Let me seems me doesn't work, yeah? So maybe
There is a Bluetooth on the side.
what he says? It's not switched. Thank you very much. Yeah. So this is, there's elementary things which is concerning relatively complicated problems with spaces with symmetry. Space with symmetry is something like that. It's a space, whatever this is, and a kind of transformation. And then we seek for objects we are invariant according to this symmetry. There's a lot of results about that, but here I want to say again some known thing. If you have a usual symmetry like point symmetry, so you have a distinguished point and you reflect all other points in that point. So that's a transformation reflection. Reflection is optical objects. But here it's not exactly optical, but it's just quite similar. And then, of course, you search for invariant according to this transformation object. So this is cycle, maybe this is ellipse, and so on and so on. There's many of such objects, but they are maybe too perfect. They are too perfect, so there are two ways of thinking. One is deform, and then if you deform, you have something more or less perfect, and then you want to do again it perfect. So there is another way. I say symmetrize. That these two opposite directions of activity, which are used usually in our research and also our life. So then here I show this center symmetry set, which was already today already appeared on some talk, but that's okay. If you deform a little bit cycle, you don't have this point of central point. You have something what is kind of central symmetry set. It depends on the deformation. Is bigger, smaller, has some structures relatively well investigated till today, also for surfaces and so on. This is the problem of fine invariance, everything. So then, if you normally you reflect according to point, how to reflect according to this set? If you deform the transformation, you can reflect. So this point in that reflections becomes not anymore point. Not anymore point if this oval is not a. Anyway, if this is cycled, then we have still the point. If this is not cycled, then we have something like that. And the reflection becomes different than point. Some structure which is depending on the something like point is lying here, around here, and then takes some information from around and reflects here. This set is invisible, of course. If you use the computing, just use computing support function, so use this computing programs, then you get something like that you have this point, and then this is a reflection. This is, I call it affine reflection. This is different than optical reflection, but in the ideas is relatively similar. It's a new notion. And this, of course, if this is a point source. If the source is not point, but more complicated, very interesting structures might appear. So some examples, if the point is close to the center, if the set is looking like that, if this is on the boundary, on this oval, it is reflected in the point on not opposite side. On the side, if this is the line tangent at that point, this is the source. If this is the tangent line of that point, then this reflected point, kind of, is here on the another line, also tangent to that oval. So this is very consistent in the notion of reflection. Okay. So we now consider the opposite direction. We have not perfect figures. Like here, we have this red figure, and that is known the parallel tangent transform, which you see, you take just these dotted lines which are tangent to this not regular curve, red curve, and you move them to around some point which is inside in the center of this interval, and you form, if you go around, you form the quite relatively very well-defined regular central symmetric object. Another reflection is, another symmetrization is this. You take the line and you take the chords perpendicular to the line transform. So then you take the line, and then you take this dotted line, and then you move it such a way that its center is on the line. And you also symmetrize this. That's obvious. Nothing especially difficult here. And but there is a third one. Oh, it's much more, infinitely many such transforms, of course. But there's another one which rather never showed up to now in the investigations. This is the, why then I explain. This is the, that you take, this is point inside the convex curve. We have this red curve, and we symmetrize in this way. This is a, this is a central symmetric transform. Central symmetric transform, we call it. So we have the such curve, and then we take a point, and then take the dotted line, in each direction, and move it to such a way that its center is in that point. So we get this blue one, which is centrally symmetric. But if we come to the other point, like here, the result of this symmetrization is no longer convex. And this is why in convex analysis, convex geometry was not much investigated because it's relatively difficult also. But this is not convex. So why this is important? Of course, we want to know what the sense of convexity. So this is also saying the kind of inside the convexity behavior inside. So then if you consider the cycle, then you, if you move that point of the symmetrization, then you get, if you are here, then you get something like some oval which is centrally symmetric and also convex. But if you pass through certain line, the dotted cycle here, then anymore this symmetrization is any more symmetric. It's not anymore convex. There are two pairs of inflection points here. And then the proposition here says, very elementary, that about to be emphasized, that for such figures, especially here for them, there is this set, we call it convex central symmetry transform boundary of this gamma curve, the red curve, which is cycle. And this, you can repeat this also to this cycle. So in fact, cycle itself, it exists in the nature of mathematics as an infinite number of cycles. With this scale factor 1 over square root 2. Naturally. Of course, it's not visible easy. Then, of course, it's easy. Some calculations. So that curves are, they calculated here. This is possible to calculate. This is some calculation that you see that some effort is done. And of course, some examples. If you consider the other curves, like for example, constant width curve here, which is here, then it depends on the point where you have. Oh, this is a point is here. You have to move this blue line to, which is the center of that. But you see, this is convex. It's convex. But if the point is close enough to the boundary, so to this convex curve, then is the image of this transform is no longer convex. So there is a question how the point looks like points, a bifurcation diagram or diagram of the points, where these curves they just pass through this that point of this higher order inflections. And this is the question to find these sets. These are new sets of affine variants of that. First, let's say we consider some simpler, well, maybe not simpler, but technical details. For example, such thing for the side two lines intersecting like here. So you have the point PQ, and you do the procedure. You just put and then you get the formula transform, and then central means that you move everything that in the half is a half of the interval, and then and then you find finally you find a transform. Here is a wings of a hyperbola, and then it is used here if you have, so for example, like triangle like this. Then your transform, if the source point is here, is never convex. It's never convex. So there are such figures that there is a transform is never convex. So that belongs to another word. But of course, if you smooth a bit this, like it here by K, say here by this equation of the triangle, it's not especially difficult, then it might appear that there is some special set where finally you get, like here, you get convexity. It is a calculation done here. And then, of course, there is a question, natural question, what happens if you pass through the curve, if you're outside of the curve? This is also interesting, because this appears that this transform, the central symmetric transform, became a kind of intersection of of it's a generic singularity of Whitney umbrella. So this is the formulation here. If P moves across C without an inflection, that we assume that this is an example of cycle here, but this is general. CST changes from two smooth branches into with two inflections each, P inside C through two smooth branches with ordinary tangency to a crossing with each branch having an inflection. In particular, for a smooth closed, strictly convex curve C and the base point P sufficiently close is never convex, the image. So the proposition sections of the standard Whitney umbrella cross cap corresponds with the local evolution of CST as the base point cross the curve. And this is in generic case, of course. Yeah. And then how it is technically calculation by hand. Or you take two branches, of the curve, but this is also for 3 dimensions, but it's more difficult. But you take two branches of the curve and you get this. One function here, G, another is F, and then you, of course, take a tidal series, jets, in jet space, and then you find you find this collinearity with origin. So you have to find at this point condition, which are the 3 points, this, and that are collinear. And this is the collinearity condition, is very important. I solve this equation according to U, and substitute into F, and you get the points of the potential set transform. And these are this equation, and then the conditions for high inflections on this transform at x equals 0. This is, you see, this is just parallelity of tangents and other derivatives. So this is first, the second, third, and the fourth later, but this is written in this on these jets, the jet coefficients here, and then you see that this is a double inflection chord relative to a given base points, a chord for which the endpoints occur at degenerate inflections. There are two points where they are the same. Because this is centrally symmetric, then the opposite points are the same. They have the same structure. And then then we ask for when there appear the singularity of the set. And then this is not yet, but as the proposition says that if the conditions 1 and 2 hold, so that the chord joining these points is a double inflection chord for CST relative to then the chord is tangent to the local CST boundary. And then singular points of this boundary of the convex set appear only when the transforms has order 4 here. If the inflection is triple, third order inflection. And so the cusp singular example fulfilling 1, 2, 3, and this we calculate also this. And what we use this in this calculation, we found the construction for the tangent line, for the tangent to the center symmetry transform. And the construction is here, is if you have this chord, the PQ, the point, and you write the central symmetry to this set. And then having this, we are able to calculate a lot. Also the algorithm for the computer. And the structure of some boundary symmetry transforms, it depends, of course, on the shape. But as you see, that there are some islands here, which have special meaning in that for these sets. Well, this is still in the process. And then, so then something like this, if you come into the boundary, you just lose the convexity. That's yeah. Yes, if this is the cases, what happens in evolving of if you move with the points P here, then there are classified possibilities. You know, this is just the collecting this inflection points. There are passings from by tangency, by transversal intersections, and so on. By inflection point, double inflection transition. Two interesting branches of C became tangent. And inflection of one branch is crossed by another branch. And this is the case of the plane. So you see, these pictures are maybe much more nicer in 3 dimensions. But a 3-dimensional case is much more difficult. Even we have not yet this tangent plane, like tangent line we had to the, which was crucial for the calculations. Usually you try to, if you find something, for 3-dimensional case, you have some computer calculations. We are able to say about some region of boundary transformations and so on. But there's a few questions. There's obviously the curves which never have points with the convex symmetry transform, but also there's a question when the boundary set is smooth. For what kind of curves? Ovals is smooth. In fact, we expect that this is very easy to answer, but still not proved on the tiles, only some calculations on computer. Oh, this is just, oh, maybe I have few minutes. So then so there are a few open questions, but this is of course not not to tell it now because the time is over. I would like to finish by congratulations to our jubilee and happy birthday, Osamu. This is the picture of your family. Perhaps girls are bigger than today. It was some years ago. They are always sweet, of course. So it was a visit of Osamu and his family to the Center for Advanced Studies. It was very nice. You see, this is a program which was very ambitious, of talks and discussions of Osamu with students and PhD students and professors and others. So thank you very much. For you, all the best and congratulations. Thank you. So, I succeed. That's it. Yeah.
Sorry, are there any questions? There is one there, one here. Yeah, you can go.
I start. Okay. How does you think the following situation may fit with your program? For convex bodies, they can be described using a support function. And this support function may be symmetric. Then you have symmetry for the points with the same tangent. Or it may be non-symmetric, and then you have a symmetric part and an anti-symmetric part. And if you just take the symmetric part, that's a sort of symmetrization, especially if the anti-symmetric part is small enough. Do you think this can fit in your different symmetrization program?
Well, you ask for interesting questions that what's the techniques used here? Of course, support functions we use, and its property are as much as possible. But you mentioned the important things, that partially the scarce objects might be symmetric already. And then there is some composition of this part, which is symmetric and non-symmetric and so on. This fits in the program, of course, but this is begging in with these singularities.
And may I ask a second question?
Yes.
If now the first symmetrization is very Euclidean, just symmetry with respect to the point.
Yeah.
Then second is more affine construction. And what about some conformal situation? And what I have in mind is the following. If you have a planar curve, you can define the medial axis. And the idea is essentially to look at the spheres, the disks, which fit inside the region bounded by the curve, and which are maximal, that is at least twice tangent. And the center of these disks form what is called the medial axis.
Yeah.
So is that relevant to some sort of symmetry which may be conformal, or to measuring the distance with respect to circles or something like that?
I know this media axis, and this, of course, this also Peter Gibrin and others, they calculated a lot of this. I'm not able to answer now, but it's a conformal symmetry. Yeah, that's a good question. I don't know. Conformal, yeah. Wojtek.
Working? Okay. Could you come back to this picture where you have this, as I understand, this is this boundary set, yes? When
Yes.
you change, no, I mean for the, before.
This one.
What you know about this singular points?
No, these are cusps. This
Cusps.
is
So you have
triple inflection points, and these other kind of swallowtails, appear, and they vanish sometimes, and they are so because this is the concrete point. But there are
So there is
swallowtail.
So can you prove that there is always for generic curve even number of them?
Because here you see
There are even number.
If there's even number, we have no such theorem.
Maybe this is
Yeah, very good.
conjecture.
This is conjecture. That's even
Maybe
number.
too much.
Very good. Today is appear one conjecture.
Thank you.
But I'm not sure. But that's likely because we have usually swallowtails. They have, of course, double fine. So that's likely. Oh.
And there is. Just wait a minute for the microphone.
Thank you so much. So we see that you start like from a convex curve. If you start from a non-convex one, so with inflection points. So if your initial curve is not convex, what do you expect for the transformation, for the transform?
Are they complex curves?
Convex.
Convex.
So you see the initial curve is convex.
Uh-huh.
It might be singular at some points, as you showed the previous.
Convex, but not necessarily smooth, yeah?
Yes, but if you start from a smooth, non-convex one.
Non-convex.
Yeah.
That's, let's say, for this talk, I wanted to be smooth.
Yeah.
But that's, of course, there are a lot of pictures which we can produce are more complicated. Yeah.
More complicated.
And this hypothesis
yeah.
is not anymore true. Yeah, because if this is singular, then of course this has some branches, and they work different way. Yeah, exactly. Yeah. Singularity cuts this set from or some sense independent objects.
Yeah.
Thank you. That's important.
Are there more questions? So let's thank the speaker again.
Okay. Yeah. Dobra. That's me. Yeah, that's
Okay, so it's my pleasure to introduce the last plenary speaker of this afternoon session. He is Roberto Jiménez Conejero. He was my PhD student in Valencia, but now he has a postdoc position in the Rényi Institute in Budapest. And his area of interest is singularity theory, focusing on singularities of mappings from Cn to Cn+1. And today he's going to speak about towards Mond's conjecture.
Thank you. Hi. Does this work? Yeah. Well, thank you very much, Juanjo, for your introduction. And I also want to thank the organizing committee and everyone that has been involved in this conference to letting me be here. It is an honor to be among such great mathematicians, especially in the occasion of the 60th anniversary of Osamu Saeki. Happy birthday, Professor. Okay, so let's talk about maths. In my talk, I'm going to deal with these kind of germs from Cn to Cp. And these guys behave differently depending on the dimension of P with respect to n. So for example, when we are in these cases where P is less or equal than n, then usually things behave in a good way. And we know, in general, that they behave in a good way. And when we are in this case, in general, we know many things and they behave in a bad way. And we will talk about this more later. And here, when P is equal to n+1, we don't know a lot of things. And I will deal with this as well. And in the first half of my talk, I'm going to deal with this case. And in the second half, I'm going to deal with these two cases. And I will say why this is bad, why these cases are bad. So, okay. To give a general flavor of what happens with map germs, I'm going to compare them with hypersurfaces, because now we are experts in hypersurfaces after the simple school. So what do we have? Okay, the first thing is that you cannot expect to have something smooth. In general, the best thing you can expect is something stable. Stable is equivalent to having A codimension 0. For example, stable germs from C2 to C3 are the immersion, the cross-cap, and if you consider multi-germs with more than one branch in the source, you have the transverse and triple, transverse double point and triple, transverse triple point. So this. Okay, so as I was saying, I'm going to compare these guys with hypersurfaces, and for hypersurfaces, we know that we look at preimages, so fibers of things, and in the case of map germs, we're going to look at images of things. And well, we know very well that the Turina number is something that is related in some sense to the space of the formations of the hypersurface. Indeed, it is the dimension or the parameter space where you can find all your deformations. So you have it here, and we have the equivalent object in map germs that it is the AE codimension, and it controls the parameter space where you can find all your deformations. So in this case, the Turina number of hypersurface would be 2 because you have here 2 dimensions, and also the AE codimension would be 2 in this case. We also know that there is a generic fiber in the case of hypersurfaces that we call the Miller fiber, and it is smooth when we talk about hypersurfaces. And for map germs, we don't have this smoothing, but we have the image, because we are looking at images of stable things, so the stable perturbation. In this picture, the Miller fiber would be something like this. This is smooth, and the stable perturbation would look like this. And observe that you don't have something smooth, you have some double points there. And we also have Miller numbers. We know that the generic fiber in the case of hypersurfaces has the homotopy type of a wedge of spheres of middle dimension, and the number of these spheres is called the Miller number. So something completely analogous happens in the case of map germs. We have the image Miller number, and we know that the generic fiber, this is the image of stable perturbation, has the homotopy type of a wedge of spheres of middle dimension, so exactly the same. So in this case, we would have that the image the Miller number is 4, and in this case, it is very clear that you have one sphere, so the image Miller number will be 2. And finally, we have a Milnor-Turina relation. For hypersurfaces, it is trivial to see that the Turina is less or equal than the Miller number, with equality in the weighted homogeneous case. But for map germs, we have this relation that the A codimension is less or equal than the image Miller number, with equality in the weighted homogeneous case. And this is only, well, there are some cases that we know, but for example, we know that for n equal 1 and 2, this is true. This is due to Damon and Mond. And in general, this is a very open question. And this is called Mond's conjecture. So I'm going to deal with a special case of this conjecture that we call weak version of Mond's conjecture. This is a result that Juanjo Nuño Ballesteros and me proved this year. And in the case of map germs from Cn to Cn+1 with finite A codimension, we know that we prove that this number is 0 if and only if this number is 0. So the inequality holds. And for example, in the case of hypersurfaces, this is trivial. If you have something that such that the Miller fiber doesn't have any sphere, then indeed you have something smooth. So this is something similar to what happens in the hypersurface case. So how do we prove it? Okay. The first thing is seeing that having something to work with the image Miller number. And in this case, we can give the image Miller number as an intersection number of two things, or the sum of multiplicity, but let's stick with the intersection number. And okay, this guy here, this is an ideal that is related to a stabilization. And what is a stabilization? It is a one-parameter family of deformations such that any deformation is stable. So something like a smoothing or something like that. And this J here is only including this space inside the family. So we have something like this. Okay, this thing here, this is a stabilization, and the first thing is J. So J looks like this. This is just the inclusion, this inclusion inside all the Cn+1 times C. So you have a copy of Cn+1 at every parameter. And to compute the intersection number, you need to move this a bit to this picture here. And we also have this variety. We need to see what kind of thing is this. So it is something like this. Okay. The first thing we need to know is what kind of points can you find in this variety. And the points you can find are, we prove that are the possible instability, this one here, and the critical points outside the image. So first of all, you have an equation for the image for this black thing here. So this equation has some critical points outside this black, this image, and you look at these critical points. All these critical points for every parameter, they are inside this variety. So you have this, and why is this interesting? Well, we know from a theorem of Dirk-Siersma from the 91 and more details that if you take the Miller numbers of the equation at those points and you sum this thing, you will get the number of spheres that you have here. So in this case, for example, these critical points would give you a Miller number equal to 1, 1, 1. So you have the 3 spheres that you can find in this image. So in a way, this variety is controlling the Miller number, because this Miller number is controlled by this image Miller number is controlled by this Miller number of the equation. The next thing we need to know is that, okay, maybe this is trivial, this is empty, and we are done. So we need to see that this is a curve. And we also prove it. So what is the definition of this ideal? The first thing is that you need to take an equation of the image of this stabilization. So you need to control all the family at once. So you take the equation G, and then you consider the projection to the parameter space. And then you can define the log of G. So first of all, the log of G is just take the module of vector fields, just that makes 0 the differential of the equation. If you were thinking about the log of a set like a Saito did, then you take, so this is the set, you would take the vector fields such that the evaluation of the differential is inside the ideal of the equation. This is equivalent to saying that the vector fields are tangent to the regular part of your variety, your set. And in this case, this is exactly the same as, okay, disregard the 0 fiber of the equation, yes.
In this, the capital F is already the whole perturbation of the map, right?
Yes.
Including the deformation parameter.
Yes.
And is it important that the vector fields are somehow tangent to the fibers of this projection, or does this not play a role?
Sorry? Is it important that they are tangent to every fiber?
Yes. Is this?
We just see that this definition works.
Okay.
But actually, we don't think about this interpretation. So.
All right. So it's the usual der log.
Not the usual der log, but the der log at every fiber, something like that. So yeah, they are tangent to every fiber. That's the only difference between, well, there are more things. That's the difference between these two guys. Okay, what do we do with this? We can define an analogous logarithmic characteristic variety, as Saito did. So if you were considering varieties, here you would have their log of x, and here you would have x. But instead, we have the equation, and we also take the log of the equation. So this is, again, just the usual, consider all the forms that make these vector fields vanish at the points ys. So why is this important? This is important because this allows us to control our variety. So you only need to think that this is related to this variety, and this is easier to study. Indeed, we prove that this guy has dimension n+3, and because we have this relation, we can prove that the dimension of this variety is 1. So it is a curve if f is unstable. Otherwise, it's empty. So we know that at least we have the instability. If we have something, we know from the previous theorem that we have a curve. And because we have a curve, we have a non-trivial intersection number. So this is saying us that because this is a curve, the image minor number is non-zero. And this is what we want to prove. If this is positive, this is positive. That's the proof. Now, there are several byproducts of this result. For example, we can prove Mann's conjecture for codimension 1 in general. Cooper, David Mond, and Roberta Vicatic, I don't know where she is. And yeah, Cooper, Mond, and Vicatic proved this result for Corang 1 singularities, Corang 1 terms. This is a general version. With this result, Houston proved the conjecture for augmentation of these guys. So we also generalize this to any Corang. And one thing that is very interesting is that this logarithmic characteristic variety is controlling more than just the positivity. It is controlling in some way the image minor number. It is controlling the number of that this is. So if this variety is Cohen-Macaulay, then for germs with one parameter stable unfolding with OPSU, we can prove Mann's conjecture. So Mann's conjecture is true. So if you have an OPSU and this guy is Cohen-Macaulay. So this is giving you extra structure. And something that was not known is that the bifurcation set is a hypersurface of pure dimension. So the bifurcation set is the parameters where you can find instabilities. For example, this parameter here has this instability, so this falls inside the bifurcation set. This doesn't, so this is not in the bifurcation set, and this also does. This is an instability. If you shake this a bit, you end up with something like this. So this is also in the bifurcation set. Some people call this the discriminant, but for several reasons, this is a better name, or this is more precise, let's say. Okay, so this was not known. Actually, in these cases, it is known that the bifurcation set is a hypersurface. In these cases, it is known that it is not, and this was not known. So, yeah. Now, the thing is, we gave a way to control more or less the image Miller number, that is the intersection number of something. But this is still not good enough, because if you have a problem and you want to deal with the image Miller number, you need something else. Maybe this is not the way to go. And how can you compute the image Miller number? Well, there are objects that are are called multiple point spaces that contain the information to give the image Miller number. And these guys are the following, or almost the following. So you take points that are mapped to the same thing. They have the same image, but the points are different. And then you take the closure of this. These are multiple point spaces. So for example, in some way, this mapping has homology. The image has homology because you have a double point. And the double point space would be AB, BA. So this homology happens because you have a double point. And this is what I mean by they give the image Miller number. Okay, why almost? Because you need an extra bit, you need a little change in the definition to have a good algebraic structure in the multiple point spaces. But I don't want to go into the details. But this extra algebraic structure means that when you have a germ of Corang 1, these guys are ICs. And we know a lot about ICs thanks to the SIMPA school. This is a result by Maran and Mond. And well, if these guys are ICs, then we are closer to compute the image Miller number. The thing is, this definition works exactly the same without any change if we have a bigger dimension. So if we are either in this case or in this case, doesn't change. There's exactly the same definition. So we can work with both settings at once. The problem is, okay, for this setting, I told you that you have a wedge of spheres of middle dimension, so you have an image Miller number. It turns out that in this setting, you also have something similar. But here, you don't have it is not clear what is the invariant to compute, to work with, or what. So in general, you can take two definitions. You consider a stable perturbation, Fs, and you can take all the Betti numbers. Because in this case, you don't have homology only in one dimension, in middle dimensions. But you have several dimensions in the homology where you can find homology in the stable perturbation. So one thing that you can do is take the sum of all the Betti numbers. Another thing that you can do is take the difference between the Euler characteristic of the special fiber and the zero fiber. So this is just taking an alternating sum with a convenient sign. This is just taking the sign of the dimension, like in the Euler-Poincare characteristic. And the thing is that both definitions coincide with the image Miller number if P is equal to n plus 1. So what should we take? Either this or this. So there are several reasons to take this one. This controls better the topology of things. And I will give you one. Houston in 97 gave the following example. This is a map germ from C4 to C6, such that the there should be an image of Fs. The image of the stable perturbation has 2 spheres and 2 3-spheres. So the vanishing image characteristic, the image, I don't know what is the name of this anymore. So this guy is 0 because you have 2 minus 2, and this guy is 4. So in a sense, this is not detecting that you have a singularity. So this is, in this sense, this is a worse invariant to take. But now, Kirk computed the AE codimension of this guy, and it is 5. And this, with this definition, the image Miller number is 4. So this doesn't hold. And in general, because this is the bad setting, the image Miller number is false for bigger dimensions. Indeed, during my PhD defense, David Mon asked me that, okay, maybe the conjecture is false, but what happens? Are there any coefficients or any weights such that when you add the weights to the Betti numbers, the inequality holds? Well, we will see that this is not the case. We can compute these guys with a multiple point space. So we go back to our previous setting. So we have this, and how do we compute the image Miller number from these guys? Well, there is an action of the group of permutations, because if you permute these guys, you still fall in the same set. So you have an action of this group. And this allows you to define the alternating homology, which I won't define now. But the thing is that there is a spectral sequence, an image computing spectral sequence, that you need to feed these guys, and it will give you the homology of the image, so the image Miller number. And several people were involved in this spectral sequence, for example, Mond, Korinov, Houston, and Jose Luis Cisneros. But the thing is, okay, now we have a way to, if you give this, I will give you that. The thing is that computing these guys is very hard in general, because there is not a good algebraic structure to say, okay, the alternating blah, blah, blah is this. No, in general, this is very hard. So we don't want this. And we can avoid using the alternating homology with the price, and the price to pay is adding more ICs. So if we consider a permutation, we can define this set. This is just the fixed points of this permutation acting here. So this, again, is an ICs in the Corang 1 case. This is proving the same paper of Mararmont. And doing a bit of yoga with the representation theory, we can prove this in the case of Corang 1. So what is this? This is just another name for the alternating homology. So this is what we want. These are ICs. This is the Miller number of an ICs, which is more or less well known. This is just a condition on the connectivity of these ICs. And this is more or less easy to compute. And these are just numbers that I won't define here. And the thing is that that is very hard, we can translate this into Miller number of ICs that are better. So this gives you a nice expression of the image Miller number. So in the case that you have a monogerm, you have only one branch, this is only the point 0, the image Miller number is equal to the sum of some, the image Miller number is equal to the sum of some Miller numbers of ICs and some 0 or 1, depending on the parity of something. So this is a very good relation. And in general, we need to take into account some connectivity thing and another thing that depends on the branches, but this is trivial. This is a combinatorial number. This is trivial to compute. And this is quite easy. So what is the takeaway of this? You can compute, or the image Miller number is determined by Miller number of ICs, in the case of Corang 1. And this is good. This is good because this allows you to do a lot of massage in things, and you are able to say a lot of things about this setting. For example, these are the germs that are a counterexample to the weak version of the Mons conjecture. So these strongly contractible germs are germs such that this is positive, but this is 0. So a counterexample of our weak version of Mons conjecture. And this is what this says. Just the image of the stable perturbation is just a point. And it is as a fun note in the several versions of the preprint, either instead of strongly contractible, I use the word disgusting, because these guys give a lot of counterexamples to many results and many things that you expect in general. And I asked some people, because disgusting is maybe a strong word, I asked some people like David and Guille for a better name, and they suggested depressing. And actually, David Mon said that he's very happy to contribute to depression in mathematics. But instead, I've gone with strongly contractible, that is more mathematical or something. Okay, so with the previous techniques, we can say when this happens for the case of monogerms. So in this, for germs from CN to CP, if this holds, you can find strongly contractible germs. So germs such that the generic fiber is contractible and are unstable. If this doesn't hold, you cannot. And these guys, these strongly contractible instabilities, they show that, okay, we know already that Mons conjecture is false, but this also shows that his question is also false. So whatever weight you take, because this is contractible, you are going to get still 0. So Mons conjecture is very false in general, not only false. So, okay. These dimensions, the dimensions where this doesn't hold are these points. For example, the first dimension where this doesn't hold is C5 to C8, that is here. And from Juanjo and me prove that when P is equal to n plus 1, you never have this. You never have strongly contractible germs. So all these points don't make this inequality true. And for example, for P equal to n or to n minus 1, this is not true. So you cannot find monogerms with contractible generic fiber. If you want to see a bigger picture of this, is something like this. This is like a fan that is midway open. So yeah. Another thing that this unexpected is unexpected homology. So if you start with instability, you don't know if for some perturbation you can find some homology. Here there is a pocket here, but you don't know if this is going to get killed when you look at the stable deformation. In this case, this homology is killed here. Here you don't have homology. So this is what I call unexpected homology, and the definition is more technical, but this is more or less the idea. And this, in fact, gives you, in some cases, this unexpected homology appears in some unexpected dimension. So in some dimension where the generic fiber is always trivial. So sometimes you find homology in weird dimensions. And you have the following. Okay. This is a conservation principle, and this is telling you the following. So first of all, this condition is where you can find unexpected homology. So this correction term is given by this unexpected homology that you have to take into account. And in these dimensions, where this is a natural number, you don't find unexpected homology, never. So you don't need a correction term. And this is telling you the following. So you start with an instability and you deform it, something like this. Something like this. but maybe you still have some instabilities. And if you take the generic, the stable deformation of this, you end up with something like this. And this should be related to this in some way. So the thing is that the total homology, so these three spheres, is equal to the homology that you already have plus the homology that is still to appear. So these instabilities will give you more homology. So this is preserved. If you keep deforming, you will end up with the whole homology. And well, yeah. For example, this tells you that you cannot expect for the image number to be upper semi-continuous. In this dimension, it will be, when this holds, and in these cases, in general, it doesn't hold. It is not upper semi-continuous. Next thing, excellency. So, again, with the same techniques, we can say something about excellency. This condition of excellent families is very related to equisingularity. So this is interesting because equisingularity is interesting. And okay, what is an excellent family? This is an example of a not excellent family. Why? Because here you have something that is splitting from the axis of instabilities. So here you have your family, and here you have your axis of instabilities. If you have something that splits, that has dimension 0, then this family cannot be excellent. However, if new things appear, but they are of dimension 1 or bigger, then this gives you an excellent family. This is more or less the intuition behind these things. So what about excellent families? Well, I proved the following. If you have a family that preserves the origin, this is a technical condition, and you don't have strongly contractible instabilities in the deformation, and you don't have unexpected homology, then the image minor number controls the excellency. If this is constant, then you have an excellent family. And so, for example, here, if this image minor number is constant, then the family is excellent. You cannot have this splitting of something of dimension 0. Indeed, without these conditions, with the condition of strongly contractible and unexpected homology, this is the statement of Husto's conjecture on excellent families. And this is false. If you don't add this is false. And this is a counterexample. From C7 to C11, this is a family, and here you have the parameter. This is a family that has 2 instabilities when t is different from 0, but the image minor number is constant, and it is positive. So what is happening is this, precisely this. You have your instabilities with constant image minor number, but you have something that splits, that is an instability, that is strongly contractible. The image minor number of this is 0. So this is not excellent, and this is a counterexample to Husto's conjecture. But I insist, if you add these conditions, this holds. Lastly, I want to talk about coalescence. And what is coalescence? Coalescence happens when, for example, for hypersurfaces, we know that if you start with a singularity of hypersurface and you have a family such that at some point you have more than one singularity, then this cannot happen. You're creating homology in the process. And this is something known from some years ago. So is this happening in our case of images of map germs? So for example, should something like this happen, that you're creating homology when you have more than one instability? Or in contrast, you have something like this. Can this happen without creating homology? This is a very hard question to answer. And for example, here you have two instabilities, and you can see that the image minor number of these instabilities is 1, because the generic fiber of this is this, and this is this. So this thing of creating homology is equivalent to say that the sum of the image minor numbers decreases by conservation. And we can state a theorem in the case of from n to n plus 1, because in general this is false. Yeah, from Cn to Cn plus 1, when n is equal to 1 and 2, so from C1 to C2 or C2 to C3, we know that this cannot happen. You cannot have more than one instability without creating homology. So something like this should happen. And to prove this, you again use all this machinery of the translating image Miller number into Miller number of ICs. I want to talk about two conjectures, just to state some problems. And I want to talk about this conjecture first. So this coalescence result, David and me have we think that we have a proof for this invariant. Here we know that this coalescence result is false because we saw, I gave you an example of this happening. You have more than one instability without changing the image Miller number. This is a bad picture because actually you won't find the homology. But yeah, in this setting, this is false. And still, we don't know if, in general, maybe if you add current 1 from Cn to Cn plus 1, in this setting where there are a lot of things that we don't know, if this holds, if you can find a family without more than one instability without creating homology. So this is a conjecture. And okay, for multi-germs, there is the question of, okay, what happens with strongly contractible? Because I show you in this fan that for monogerms, we can know exactly where these strongly contractible instabilities are. But for multi-germs, we don't know. And actually, I have the suspicion, for several reasons, that if this doesn't hold, you can find strongly contractible germs. So instabilities such that the generic fiber is contractible if this doesn't hold. And well, I think this is all. Thank you very much.
Sí. Okay, thank you very much, Roberto. Any question or comment? Yeah.
So I think these are really nice results, but it leaves me with a negative feeling in that it looks like if you want to have a family of maps that is relatively well behaved, then the image Milner numbers are not going to be enough. So what do we have to add to make sure that things are excellent?
Well, it is not enough in this case. Because in this case, Juanmi, for example, proved a theorem that we can use a mu star sequence like this here. Well, we need 2. So we have some invariants related to the image Miller number that are enough in current 1 to control the equisingularity in this case. In this case, I have no clue. Well, you have a theorem about this, but in general, I don't know. And indeed, the image Miller number is not enough.
Yes, Christian?
My question is relating the definition of strongly contractible. I was wondering, will it be necessary to check the contractibility of every disentanglement, or it is enough to check for one given disentanglement, perhaps with some nicety conditions?
Okay, for strongly contractible, what usually is called the disentanglement is the image of the stable perturbation. Every image of every stable perturbation is contractible. Mm-hmm. But if you take a not necessarily stable, you can find this unexpected homology in some cases. So it is not true that if you have a contractible generic fiber, every fiber is going to be contractible. Sometimes it is not. And there are examples of this in my preprint.
So you need to check every fiber then?
Well, what do you mean by you need? So usually we study only the stable perturbation. And this is known to be contractible. Yeah.
Okay, thank you very much.
Thank you, Roberto. A nice talk. Can we look at the Kevin Houston's example again, please? So,
do you remember what?
I wonder. Think later, right? Later.
No. Sorry. You mean the counterexample to the
The
contractor?
counterexample to the contractor.
Ah,
yes.
okay,
Yeah,
okay.
from C4 to C6, right?
Yes. This one.
Yeah. So my question is if this is a genuine example in the sense that, well, not this one, is the one that the A equal dimension is 5, right? And the Milnor number is 4, right?
Mhm.
So my question is if there is modality, I mean, if there is a straton or if this is a simple singularity, you know, because it could be possible that the codimension of the strata containing the singularity would be 4. So that's the question. Or this is not the case, and then it would be a genuine counterexample.
I strongly believe that you can find genuine counterexamples. In this case, I don't know. But yeah, I think we can find counterexamples with the same thing, but not necessarily with modality.
Oh. Well, in fact, my other question, if I can ask another one, is similar. When you have a strongly contractible singularity, the first thing we can think is that when you look at the stable unfolding, that this stable unfolding is topologically trivial, right? So in a sense, my question is of the same kind. So do you expect that this is what will happen there, or in fact you can have more similarity splitting and zero Milnor number?
Sorry, can you repeat the question?
Yeah, in those examples
Yes.
in which you have strongly contractibility without stability, right, with zero Milnor number,
Yeah.
my question is, do you expect that if you look at the stable unfolding, this stable unfolding will be topologically trivial?
No, I don't, for this reason, because there are some, well, I don't know, but there are some perturbations that have homology. And this homology, if you keep deforming things until you have something stable, this homology is killed. And I expect that this is not trivial because of this new homology that appears and maybe disappears.
Okay, thank you. This is.
You have this bound for the possibility of existence of strongly contractible singularities, right? First question, because maybe I missed out on this. Does this no? Or maybe no. Maybe you can say this. Where does this bound come from? Does it involve the ICSS?
Yes, in the sense. So this. Well, this.
Yes.
Yes, in the sense that the multiple point spaces, you put them. Well, you put the alternating homology in the ICSS.
Yes.
So you put them in the spectral sequence, and they give you the image, the homology of the image. So the thing is, this bond comes from all the equations. You need to take care of all the equations of all the equations of the multiple point spaces. If you can find multiple point spaces that are smooth, they won't give you homology, so this is not contributing to the image. But if you find multiple points of expected negative dimension, this says that you have an instability. So you can have an instability with all the multiple point space that contribute to the image being smooth, but some other multiple points that are not smooth. And these guys don't contribute in the ICSS. So this comes from the equations of the multiple point spaces.
And is this all for core rank 1? Or can you even say something beyond core rank 1?
No, because if you don't have something of core rank 1, multiple point spaces are horrible. And you don't know. So the thing is, if you have something that is smooth, the Miller number is going to be 0. So the alternating homology is going to be 0 because of this relation that I showed. But in general, that is not enough. I mean, you can have homology in bigger core rank without having alternating homology. So it is not enough being smooth. Being smooth is too strong. So this is not how you should compute things if you don't have core rank 1.
Okay. And one last thing that I probably missed is, do you have examples for all the blue dots to
Yes.
find the contractible thing?
Yes, the examples are outside the blue dots. The blue dots are where this doesn't hold. And I give a constructive argument to show that in all these dimensions where this doesn't hold, you can find a strongly contractible germ. And outside you cannot. And the thing is, so this example is not random. You have something times y plus y to the 5, something times y plus... It's something like this. With some trick like this, you can find strongly contractible germs if you have enough variables. And this is the point.
All right. Good. Thanks.
Thank you.
Okay, so anything else? Yes.
Yes. Can you come back to the slide of Mon's question? This about the shifting in the coefficient of the... Yes, this one. And the countersample you show is a case where this mu tilde is 0, no?
Yes.
And can you find a contraexample when mu tilde is not 0 to this question?
I tried to find a family where this relation is smaller, something like that. So where this doesn't hold, but this is difficult, and I don't know if that can be done.
Okay. Okay, good.
Could you please go back to the slide where you were plotting the points where there was something that was strongly contractible? Let's see. It was the graphs of the. There we are. There seems like there's a gap in there. Is there an explanation for that? Are those places where you just haven't found examples yet, or?
Sorry, where? Here, for example, or here?
Yes, there's no dots there.
Yeah. If there are no dots, this means that you can find strongly contractible germs. And this is an if and only if. If you have a dot, you cannot find a strongly contractible monogerm. If you have not, you can find. And the reason of these gaps here and these gaps is because you have this floor function. Nice, a lot of questions.
Okay. Your strongly contractible germs, are they finitely determined? I don't know if you
Yes,
said.
by definition.
And is there a bound on the codimension in order for them to appear?
I suspect there is no bound.
So in low codimension, you can find things like this. And in arbitrarily high codimension, you can also find
I
things like
think, but I need to think about this, but I think that's the case.
And is it related to the nice dimension in the sense of, do you need the existence of a stabilization or something like this?
I don't think so because as we are in current one, you can get outside the nice dimensions. I don't think this is very related, but I don't know.
Okay, okay. Thank you.
Okay, so if there are no more questions, let's thank Roberto again.
Thank you.
Everyone that will present talk or post a presentation will get diaries, okay? But we of course is having some problem just to get the fund, but it will come. But anyway, if you want to go to join to the lunch on Wednesday, you can just allow the help desk to discount such a amount from your diary. Okay, you don't need to have the cash right now. Okay, just this quick info. Okay, bye. Thanks. See you tomorrow.